All right, section 2 involves solving exponential equations. That's what we're going to do here. The property of equality of exponential equations says that if b to the x equals b to the y, if and only if x equals y. Okay, so basically if you have an exponential equation where the bases are the same, then the exponents must also be the same for them to be considered equal to each other. Okay, the trick is getting those bases to be the same at the outset. So first example we have here, this one's pretty easy because the bases are already the same, they're both 3. So this must mean the exponents have to be equal. X equals 5. All right, pretty straightforward there. That tells us that 3 to the 5th equals 3 to the 5th. All right, let's try a couple more difficult ones here. So we've got 2 to the x equals 8 to the 3rd. So our problem is that the bases aren't the same. Okay, but usually when this happens, one of the bases can be converted into being the same. So we can't convert the 2 because we can't really break down 2. But 8, we can break that down. 8 is 4 times 2, and 4 is 2 times 2. So 8 is really 3 2's, or 2 to the 3rd. So I can rewrite this problem as 2 to the x equals 2 to the 3rd to the 3rd. Okay, so the 2 to the 3rd is because there were 3 2's here, and then the other third is from the problem, this third power on the 8. So you can use your exponent rules that we went over a couple weeks ago. 3 to 3, power to power rule. We multiply there, 2 to the x equals 2 to the 9th. And so that means that x must equal 9. All right, let's try one over here with a little more algebra in it. So same deal, the bases aren't the same. 3 can't be changed because it's already a prime number, but 9 I can break down to 3 times 3. That's 3 squared. So this is 3 squared to the 2x minus 1 equals 3 to the 6x. All right, power to a power rule says I multiply these two exponents, so I'm going to have to do some distributing here. 3 to the 4x minus 2 equals 3 to the 6x. So that must mean that 4x minus 2 equals 6x. And I can move that 4x over. Negative 2 equals 2x, and then divide by 2. So x equals negative 1. All right, let's try an application problem with this. Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. Write an exponential function that could be used to model the number of bacteria after x hours if the number of bacteria changes at the same rate. All right, so we're writing this function here. So we've got y equals a b to the x. All right, this is your general form of an exponential function. All right, y is how much we have at the end. So they tell us that after 4 hours, you have 23,000. So 23,000 goes in for y. A is your initial amount, so that's going to be the 7,500 that we started with. B is your growth or decay factor, growth in this case. We don't know what that is yet, so we're going to leave that as B. And then we're going to raise it to the x. X is the number of hours, but they told us that, and the problem is 4. So let's start out by solving this for b. We need to know what b is to write a proper equation. So I'm going to divide by 7,500. All right, calculator is going to come in handy here, so let's pull that up. And I've got 23,000 divided by 7,500. And then control enter to get a decimal. So 3.07 approximately equals b to the 4th. All right, and then we got to get rid of that 4th power. So to get rid of an exponent, you take the root, 4th root of that number. All right, so to do a 4th root, you press control and then the exponent key, which is this. Type in the index you want. We want 4. And then for this part, we want to copy that number down hit enter. So 1.32 equals b. Approximately, so put a wavy sign. So to write the full equation, y equals 7,500 times 1.32 to the t, or to the x. All right, part B. How many bacteria cells can be expected in the sample after 12 hours? Well, x is our number of hours, so they just want us to plug 12 into our equation that we've written, figure out what it equals. So y equals 7,500 times 1.32 to the 12th. All right, we'll probably be estimating here, so let's type this out. We've got 7,500 times 1.32 to the 12th. 209,869. Cells. All right, another application of these is compound interest. This is something that pretty much all of you are going to encounter at some point. Any savings account, anytime you put money into a bank and it earns money on its own, all right, that's compound interest. And it's very, very powerful because if you start early, the money really starts increasing a lot in your later years. Okay, that's compound interest is super powerful in that way. So this is the equation for compound interest, kind of a complicated one. I've written what all the letters mean over here. All right, so they're going to give us basically 4 out of the 5, and we can plug them all in, and then we'll be able to figure out what the answer is to the problem. So an investment account pays 4.2% annual interest. Remember, when we deal with percents, we're going to move that decimal over, so we're going to use 0.042. All right, that's our R. Compounded monthly. So N is the number of compounds per year. Well, how many months are in a year? 12. If 2,500 is invested, so that's our principal, the initial amount, what will be the balance after 15 years? And that's our T. All right, so they want us to find the amount, A. So A equals 2,500 times 1 plus 0.042 over 12 to the 12 times 15. All right, we'll use our calculator here again. 2,500 times, make sure to put this part in parentheses, 1 plus 0.042 divided by 12. And we'll close our parentheses, and then we'll raise it to the power of 12 times 15. All right, so after 15 years, that $2,500 would become $4,688.87. So this equals $4,688.87. All right, this last part is inequalities. This is only for pre-AP, so if you're regular and you're watching this, you can stop. All right, pre-AP kids, keep watching. We're going to do a couple of inequalities. Okay, so we have the property of, I should have put inequality there, property of inequality of exponential inequalities. All right, and it's pretty much the same thing we saw before. So if b to the x is greater than b to the y, if and only if x is greater than y. And similarly, b to the x is less than b to the y, if and only if x is less than y. Okay, so it just follows along. You have to have the same base, and then you follow it from there with the exponents. So on this one, again, our easy example, we have 2 to the x is greater than 2 to the 6, so that must mean that x is greater than 6. All right, let's try to get our bases the same here. So we've got 16 and 8. All right, this one's kind of tricky. So like 16, the first thing I notice is like it's 4 times 4. That's 4 squared. But can I get 8 to be 4 to the anything? No. Okay, so we have to go a little bit further. Both of these 4's break down to 2's. So another way you can write 16 is 2 to the 4th. Well, I can also break down 8 into just 2's. I can write 8 as 2 to the 3rd. So let's do that. This is 2 to the 4th to the 2x minus 3 is less than 2 to the 3rd. All right, we got to do some distributing here. So that's going to be 2 to the 8x minus 12, which is less than 2 to the 3rd. All right, let's come up here and give myself a little more room. So that's going to leave me with 8x minus 12 is less than 3. Add 12. 8x is less than 15, and divide by 8. X is less than 15/8. All right, last one over here. This one's a little tricky because of the fraction over here. Okay, but what you want to see is that 243 is 81 times 3, and 81 is 9 times 9, and 9 is 3 times 3. So how many 3's is that? 1, 2, 3, 4, 5. So this is the same thing as 1 over 3 to the 5th. Still not exactly what we want. We want the base to just be a 3. All right, so what I'm going to do here is move this 3 to the 5th up to the top. And what happens there is the exponent becomes negative. So that becomes 3 to the negative 5. Okay, you can verify this in the calculator. 3 to the negative 5, 1 over 243. Okay, so just look out for things like that. They like to throw those fractions in. Those are always going to give you a negative exponent when you get a fraction like that. All right, so we have the same base, so that must mean 2x minus 1 is greater than or equal to negative 5. Let's add 1. 2x is greater than or equal to negative 4. So that must mean x is greater than or equal to negative 2.